So this one's a little different, a different type of math. For lack of a better phrase, let's just call it counting. Okay. So, I used a couple of examples. Let's say I've got these row of 5 here. Okay. How many different ways could I arrange them? Like, how many different ways could I seat them? I'm trying to count how many ways. That's a counting problem. And we'll figure out how to do it. Okay. What's that? That's correct. Okay. Don't worry. We're all going to know how to do that. We're all going to know how to do that. Okay. Another type of counting relates to probability. And another question, if you're familiar with Lotto 649, when you buy a ticket, you pick 6 numbers out of 49. When they do the draw, they randomly choose 6 numbers. What's the probability your numbers match? Okay. Well, that's going to be 1 in over 13 million. That's why it's hard to win. Okay. Those are just a couple of counting examples. We're going to do a little algebra towards the end of the unit where we can use counting to help us do some algebra. But in the meantime, the first 3 lessons, we're going to there's going to be a lot of word problems. Okay. So counting methods are used to determine the number of members in a specific set, as well as the number of outcomes of some events. So let's start with a pretty straightforward example. A restaurant has the following options for pizza. For meat, and we'll keep it simple. For meat, you can only choose pepperoni or bacon. For vegetables, you can only choose onions, green peppers, and mushrooms. The lunch special requires you to order 1 meat and 1 vegetable. How many different pizzas can you make? Okay. Well, we're going to start with that one, but then we're going to leave it. So if the numbers are really small, like we've got 2 types of meat and 3 types of veggies, yeah, we could do that. We could say, okay, let's say you chose pepperoni as your meat. What are your possible choices for a vegetable? I could go pepperoni onion. I could go pepperoni green pepper, and I could go pepperoni mushroom. So if I choose pepperoni as my meat, there's 3 different types of pizzas I can make with 1 meat and 1 vegetable. If I go back to the meat and say, okay, this time, bacon. What are the possible vegetable choices? Same. Onion, green pepper, and mushroom. So therefore, there are 6. Right? 1, 2, 3, 4, 5, 6 different ways I can make the pizza. But mathematicians are lazy. We want to look for a quicker way to do things. So we can do it like this. When I make a pizza, it is made up of a meat choice and a vegetable choice. How many possibilities are in this choice? 2, because there's 2 meats. How many possibilities or choice are there for the vegetables? 3. To find both, multiply. And you get 6. Much quicker. Okay. So if we're dealing with small numbers, we could write out all the possibilities using the tree diagram. However, the bigger the numbers become, because obviously there's going to be more meats that you could choose from, and there's more vegetables. So like if, you know, you had 5 different meats and 8 different vegetables, okay, how many possible pizza combinations could you make? Well, drawing a tree diagram would take a long time, but you just do 5 times 8. There's 40 different ways. Okay. And this idea of just using multiplication is called the fundamental counting principle. And what does it mean? If we can choose one item in a number of ways, and the second item can be selected in B number of ways, the ways I can make them together will be A times B. So for example, here's another one. While backpacking in Europe, Herman bought 4 shirts, 5 pairs of shorts, 3 pairs of shoes. Brought, okay. How many different outfits can he make? Well, I need a position for the number of possible shirts, the number of possible pairs of shorts, and the number of possible pairs of shoes, and together I multiply. So it's going to be 4 times 5 times 3. 60 different outfits. Okay. So we can apply this type of counting to a whole bunch of different problems. Let's take the situation here, where we'll do, I'll ask you a few. How many 3-digit numbers can you make using the digits 1, 2, 3, 4, 5, 6, 7 without repetition, meaning you can't use a digit more than once? So your number can't contain 2 1s or 3 1s or 4 2s. It can only contain one of each. Well, I'm making 3-digit numbers. So I'm going to put a position for each digit because there's a certain number of digits I can use for each position of the 3-digit number. Let's start on the left. How many possible digits could I put in here? 7. This is important. Without repetition, which means the next one is 6. Because whatever number this is, you can't use it again. So it's 7, 6, and following the same reasoning, 5. So you get 210 ways. How many of the above 3-digit numbers are even? Notice what I'm doing. Always fill in the restrictions first. So I'm not going to start on the left side this time. I'm going to start here because this has to be even. How many possible numbers could go here if it's even? 3, 2, 4, or 6. Now go back to the left. I've used one of the numbers up. How many are left to use? No. No. All the other numbers come into play. 6. Isn't it? I've used one number here. 2, 4, or 6. So that means there's 6 numbers left I could put in here. Yes, like if I put 2 there, don't I have 6 to choose from now? Yes, that's what this takes care of. This doesn't have to be even. The number has to be even, which means it has to end in an even number.
Why wouldn't you put 7 in?
Because you've used one of the numbers here.
Well, why don't you, like I'm saying, like, why can't you put 7 or 6 in?
Because I've started here and I've used a number. I've used one of the 7 numbers, specifically 2, 4, or 6. So let's say that I use 2. How many numbers do I have left to put in this position? 6. Let's say I use another number. It doesn't matter whether it's odd or even here. How many numbers are left? 5.
Yeah.
What makes an even number? What does it have to have at the end?
Not 3.
Why don't you tell me what it has to have instead of what it doesn't have to have? But here's are the only ones I can choose from. To make it even, doesn't it have to end in a 2, a 4, or a 6? Which means I got to choose one of those 3. That's why it's 3. Yes, because it doesn't matter what these are. It's the last number that makes a number even. Like this. Fine, this is even, but the number's not. The number's odd. Why? Because I only look at the last one. Okay? So, how many are odd? Again, start with the restriction. What are the possible numbers from these to choose from will make the number odd? 4 of them, 1, 3, 5, or 7. Okay? I have now used one of them, which means I have 6 left that I could put here, and then 5. Getting a little better? Okay. How many numbers are greater than 300? So the restriction is here, isn't it? It has to be a 3, or what else could it be? It has to be greater than 300. It could be a 4, 5, 6, 7. So there's 5 possible choices. I've now used one of them. How many digits are still left to use? 6. And then 5. Now you get it. And that works out to 150.
How can you use 5 twice?
You're not, I think you're confusing these between the number of possibilities and the actual digits. Yes. It depends on the question being asked, right? Like if it talks about an odd or even number, I got to go to the end first. If it talks about being less than or greater than some number, I got to go to the beginning first. Let's try another one. How many different 4-letter words? Okay, so a word could be nonsensical. Can I use making the letter or use with the letters A, B, C, and D? A letter cannot be used more than once. So I'm making 3-letter words. So for example, ABC would be considered a word, even though it's not an English word. Oh, sorry, 4 letters. So there's no restrictions. So I can start here. How many possible letters?
4.
Then, boom. 24 waves. Yeah.
How do we know how much 20 is if there's 5 schemes?
Times 4, times 3, times 2, times 1. Yeah. What about if I said, if I lined, how many students are in senior school? I don't know. Let's say 180. What if I lined all 180 up and said, how many different ways can I arrange them? 180 times 179 times 178. That's a lot of multiplying. Fortunately, there's a short form that we can do. There's a function on your calculator. If we take a number times 1 less, times 1 less, times 1 less, all the way down to 1, that's the same as this. An exclamation mark. So 4 exclamation mark, relax, means 4 times 3 times 2 times 1. 180 exclamation mark means 180 times 179 times 178, all the way down to times 1. Okay? That is given a certain name. This is called factorial. And it saves us some time. In these type of questions, factorial is really not going to help very much. Okay? If anything, plugging 4 factorial into your calculator will take longer than doing 4 times 3 times 2 times 1 in your head. So in general, if I take some number factorial, I start with that number, then I times 1 less than that number. Then I times 2 less than that number. And then I keep times 3 less, times 4 less, until I get all the way down to times 1. So 8 factorial means 8 times 7 times 6 times 5, 4, 3, 2, 1. Okay? I'm not going to explain this in the interest of time, but 0 factorial is always 1. Now, to work with factorials, there's something you got to know. If I said, say, 9 factorial, that is the same as 9 times 8 times 7 times 6 times 5, all the way down to times 1. It's also the same as this. I could do that. 9 times 8 factorial. Doesn't that mean 9 times 8 times 7 times 6 times 5? I'll show you where we use it in a second. Or I could do this. I could just keep counting down, and whenever I decide to stop, put a factorial there. That just means you keep going. So I could do 9 times 8 times 7 times 6 factorial. I'll show you, again, I'll show you why that works, or why we use that in a second. If I use a variable, n factorial can be the same as n times n minus 1, and to keep going, I just put a factorial. Or it could be n times n minus 1 times 2 less, and then if I decide I want to stop, I have to put a factorial at my stop. And we can only take the factorial of whole numbers. Okay, so here's how we can use it. Like this. 10 factorial times 9 factorial. Can you think of a quick way that I could find this answer by using what I just showed you? Why not do this? Start writing the 10 down until you get the same number as the denominator, and those are going to cancel each other out. 10.
That actually makes sense.
Let's look at this phone. This one, what would you do? Take the bigger one and start writing it down until you get the smaller one. So I'm going to take the 7 factorial and start writing it down until I get 5. Those cancel. Remember, there's 1 at the top. 1 over 42. This one, 12 factorial over 8 factorial times 4 factorial. Well, I could start doing this. 12 times 11 times 10 times 9 times 8. Put a factorial there so I can cancel it with the 8 factorial on the bottom. Well, that's still a fair amount of calculation. That's still 12 times 11 times 10 times 9 over 4 times 3 times 2 times 1. I could do some more reducing. Or just, in this case, you wouldn't see a question like this with no calculator. So you could just multiply this, multiply that, 24, whatever this is, divide 24, and you get an answer of 495. But that wouldn't be, yeah, if you were asked to do that, that would be in the calculator section. Now, these two are a little different. Because they have, instead of a number, a variable. Well, take the bigger one and start writing it down until you hit the smaller one. And then put a factorial so you can cancel them. What's the bigger one out of n and n minus 2? N. So start writing this down. N times n minus 1 times n minus 2. Found a match. Stop. Those go. And I'm just left with n times n minus 1. You don't have to multiply through. Be careful with this one. What's the bigger one? N minus 4 is the bigger one, right? So for that, you got to go n minus 4 times n minus 5, which is 1 less. Matches the denominator. Stop. Cancel those two bad boys out, and you're left with n minus 4.
You know, my brain isn't letting me.
So you can see where we can use these things. And one area of counting where we can use them is something called a permutation, where you are trying to find the number of arrangements of something in a specific order. To permute a set of objects means to arrange them. Okay. So consider the letters A, E, and T. List the different ways to arrange them. In other words, how many 3-letter words can I make from A, E, and T? You guys should be able to go to the counting principle. How many different letters here? Then equals 6. And there are 6. If I started with A, I could do AET. I could start with A again and reverse the E and T. There's no other ones I could make starting with A, so I'm going to try the one starting with E. Well, I could make EAT and flip the T and A and T for me, and get easy, get ETA. And then T, and for lack of a better thing, tie. Okay. Okay. Or we can use a permutation formula. Okay. In other words, how can I arrange R objects from N? This is a formula you will get on your formula sheet. To do that, we use factorial. We take the total number that we're choosing from, factorial, divided by the total number minus how many ways we're choosing, factorial. Order matters in permutations. We'll see that when we talk about combinations a little bit down the road. Okay? N always has to be greater than or equal to 0. Always. We can't do negatives. Okay? You can't say how many ways can I arrange -5 from -7. Doesn't make any sense. -7 objects. Yeah. Yes. But N always has to be bigger than R. Okay? Or equal to. So you could have 0p0. But then you can't have 0p1 because then that's saying how many ways can you arrange 1 from nothing, which doesn't make sense, right? So let's look at an example. If there are 7 members on the student council, how many ways can they select 3 students to be the chair, secretary, and treasurer? So the order matters. Okay? Whoever's first is the chair. Whoever's second is the secretary. Whoever's third is the treasurer. So we can use the fundamental counting principle to do it, which I would highly recommend, to be honest. I would always use this method over this formula. Okay, but I'm still going to show it to you. So I've got 7 people. How many possible choices are there for the chair? 7. So somebody's been appointed the chair. There's only 6 left to appoint the secretary, one of those, and then 5. And we get 42 times 5, which is 210. Here's how we would do this one. We would say to ourselves, how many ways can I arrange 3 people from 7? I'm kind of working backwards. How many ways can I arrange 3 people from 7? So following the formula, it would be 7 over 7 minus 3 factorial, which is 7 factorial over 4 factorial. And remember how we simplify these? 7 times 6 times 5 times 4, stop so I can cancel with the 4 factorial in the denominator. And look what I'm left with, 7 times 6 times 5. But you can see how in this kind of example, this is way more efficient. Okay. With larger numbers, this would become more efficient. There is actually a function you can use on your calculator for it. I'm not going to worry about it with permutations. I'll show you with combinations. Okay, finally, we can use this formula to do some algebra. Okay. What does this look like if I use the formula? Is this not the same as I take the first value here, n, over n minus 2 factorial? Right? That's using the formula. I replace n with n, and I replace r with 2. That's going to equal 30. Well, how do I solve a factorial equation? I got to get rid of the factorials. How do I get rid of them? N, take the bigger one and start writing down. N minus 1, n minus 2, stop there, bless you. So I can cancel the bottom. Notice the factorials are gone. So I'm left with n times n minus 1 equals 30. I have to solve this, get rid of the parentheses first, and it looks like this. You should be able to tell me where to go now. Yes, it's quadratic.
Yes.
Everything to one side and factor.
N squared minus n.
N squared minus 30 equals 0, and then you're ready to factor.
Woo.
-6, +5. Therefore, my two possible answers are,
Wow.
does anybody have an issue? It can't be negative. Right? N can't be negative. So there's only one answer. Yes, 5.
Good job.
All right, this one.
Nice.
So I got to use the formula to write this using factorial. So I take this, n minus 1 factorial, over n minus 1 minus 2 factorial. Equals 72. Well, I got to do some simplifying here. What's an easier way to say the bottom inside the big parentheses? N minus 3. Now I got to cancel out the factorials because I can't use them in my equation. So I need to start taking one of those, writing it down until I can cancel it with the other one. Take this one and start writing it down. So n minus 1 times 1 less, n minus 2 times 1 less, n minus 3. Stop there because it matches with the denominator n minus 3, which means those can go. Notice when I get rid of the parentheses on the left here, I'm going to get a quadratic again. 4 multiplications. N squared minus 2n minus n plus 2 equals 72. That's nice. Now, n squared minus 3n plus 2 equals 72. Bring the 72 over. And I get one I can factor, and this can be factored. Got to think of what multiplies to get 70. 10 and 7 are going to work. Which one's negative? Negative 10, positive 7. Therefore, n is equal to 10 or negative 7. And to have negatives, remember that's the same like as logs. So we take it away.
We're done now.
One like this seems to appear on every sort of second provincial. I wouldn't be surprised to see one like that.
Oh,